So, it's continuing with our work, progressing through a variety of different functions and understanding the basics of a variety of functions. The last couple of lessons were focused on quadratics. I have a little bit here, and then I want to introduce cubic functions and especially power functions by the end. First, a fairly typical example of a quadratic function being used in a problem. Looking at some basics of physics here, but a man who is 2 meters tall throws a ball straight up in the air. The ball's height above the ground at time t seconds is h equals 2 plus 9t minus 4.8t squared. And so this here being a quadratic function, and we're asked to do a few standard questions based on this. First being, what's the time in seconds? What's the time in seconds it takes for the ball to reach its maximum height? Followed by, what is that maximum height? Well, both these ideas we can figure out from finding the vertex of the graph. And quadratic functions should be easy to graph. And so if you graph this function, most likely you would graph y equals 2 plus 9x minus 4.8x squared. Should see something like this. And the vertex tells me both the time it takes for the ball to reach its maximum height as well as the height it reaches. And so the x coordinate, that's negative 9.38, just shy of a second. So it takes just shy of a second for the ball to reach its maximum height, and that maximum height is just over 6.2 meters. And so just from that, I can answer both these questions. And so the time, and again, this is from the graph for all of this actually. So the time is approximately 0.938 seconds. And from the graph, the height is approximately 6.22 meters. So I'm just putting everything to 3 significant figures. Now finally, it asks, after how much time does the ball hit the ground? Well, again, we can find that from the graph quite quickly. If I just go back here, it hits the ground when the height reaches 0, which is right here. That's when the x-intercepts. And so just past 2 seconds is when it hits the ground. And so keep in mind the other x-intercept is not necessary in this question. That's before it left the person's arm. So this, that value is kind of meaningless in this context. So just 2.0, I'll round it to 2.08 seconds to put it to 3 sig figs. Now keep in mind, if you didn't want to solve these by graphing, this here we could have solved by, that's the same as one of the x-intercepts, so we could have solved that by using the quadratic formula or by factoring if this could factor, but this doesn't look like it factors nicely. And the vertex here we could have found by completing the square. However, all of that would have taken no matter how much you've practiced those sort of things, graphing it is definitely faster and gives us the same level of accuracy. And would be encouraged to graph it. Okay, moving on to beyond quadratic functions. I have a cubic function here, minus x cubed minus 3x squared plus 3. And I want to sketch it. And so, again, it even says here, use your GDC. So remember, when we want to sketch something in an IB class, we're being asked to sketch, we want to think about the general shape as well as any intercepts. And we can see there's 3 x-intercepts here and 1 y-intercept. And so in terms of sketching this, we don't need to worry about making it to scale, but we do want to show the general shape. We want to show that this has no global maximum or global minimum. It goes up forever, it goes down forever. Although in this vertex here, we could show that as well. It's actually at a pretty nice point, so maybe I will show that. And I'll just kind of sketch this out. But essentially, I'm kind of just copying the basics of what I see here. And so those basics being the x-intercepts. So there were 2 negative x-intercepts and 1 positive x-intercept. All of these are rounded to 3 significant figures. There was 1 y-intercept, which was at exactly 3. And then there was that general shape in which it came down, had a turning point down here, went back up. If I look at my graph, it does look like this y-intercept is also one of my turning points, one of my vertices. Just don't expect the y-intercept to have to be a vertex. It's quite like, almost certainly it's not usually the case, but in this case, it is one of my vertices. And so I'll show it reaching a turning point here, and then going down, and then just keeps going down. So to show my end behavior, we say with these arrows that it just keeps going that way forever. And I'll show this vertice right here as well, which was at -2, -1. Although in general, when you're sketching a function, the most important part is the general shape. Your x-intercepts, or your zeros they're called, and your y-intercept. And that's all kind of sketched out. All right, so the last thing I want to look at are power functions. And so what I have here are a variety of different but very similar power functions. There are 2x cubed, 2x to the power 4, 2x to the power 5, and so on. And so the definition of a power function is it has to be something in this form where you have some constant or coefficient, I should say, at the front. Your variable is the base of, in this case it's x, the variable is always in the base. The exponent is a constant, but the exponent can be any real number. It doesn't have to be a whole number, it doesn't have to be a positive number, it can be any real number. And that's actually what we see up here to be a power function. Your exponent, n it says here, can be anything, any real number. So negative, positive, integer, rational number, irrational number, anything that's real we can have there. And a, though, can be any value as long as it's not 0. And so what's described in these points after that are some of the general characteristics of what we notice with different values of a and n. And so I'll just kind of come here. And while we can graph all of these with our GDC, ideally after a while we can kind of see we can see some certain characteristics coming up. And so for 2x cubed, I'll just graph that here for now. So 2x cubed looks like this. I'll just go to a basic zoom. I'll zoom in a bit. And one x-intercept, one y-intercept, same spot in the middle. Pretty easy to sketch out. That said, when I go to 2x to the power 4, I get a distinctly different graph in some ways, but has a lot of commonalities. So for this one, I'm going to go here. I'm going to move this up to a 4. You know what? That's needlessly complex. Maybe I'll just change it. I'll just change this to a 4. Let's just do that. I'll come back to this later. So here's 2x to the power 4, which instead of starting in quadrant 3 and going up to quadrant 1, it starts up in quadrant 2, comes down, and then goes right back up. It's almost like a parabola. It's similar. It's not a parabola, though. This shape here is not a parabola. If we look at the shape around the vertex, a parabola doesn't have this sort of flattened out vertex here. So it has aspects of it, but this is not a quadratic function, and this is not a parabola. What if I go to the power of 5? If I go to the power of 5, it's now suddenly looking quite similar to the first thing I drew. It's not the same. In fact, if I show both these at the same time, I'm going to make this n of 3. What you're seeing here in purple is 2x to the power of 3. What you're seeing in green is 2x to the power of 5. They're very similar, but they're not exactly the same. Although when I sketch out 2x to the power of 5, it's going to look kind of the same thing. I mean, if I'm just making a sketch, for all intents and purposes, you can try to make it a little more flat looking here, but really, it's exceedingly similar to what we had for 2x to the power of 3. Which means you can probably guess that 2x to the power of 7 is going to be like that as well. It's going to be a little more extremely horizontal-ish, although it never actually is horizontal at any given point. And it's going to be, if you look at 2x to the power of 3, 2x to the power of 5, 2x to the power of 7, they're all very, very similar. They're all slightly different, but if I kind of go here now and make this a 7 here to kind of compare, notice 2x to the power of 7 is different again. It looks quite horizontal here, although if I zoom in, maybe I'll turn this one off. If I zoom in, you'll notice that it's never actually horizontal, although it's getting so close, it's hard to tell that it's never actually perfectly horizontal, but it's always getting slightly closer. However, in the long run, if you look at these odd-numbered powers, if I did 2x to the power of 9, I think you can guess how it would look. 2x to the power of 17. And in general, you can see here as I make these powers, if I bring this to 2x to the power of, how about 75, it looks quite similar. You may think these are right angles. They're not. If I zoom in, you can see they're not. But in the end, it has that same sort of behavior. And the bigger the number, if I make this 2x to the power of 751, it's no longer really looking much different. Although that's kind of I'll just go back to a 7, and that covers our odd numbered powers. Even numbered powers, we get the same sort of idea. We've already seen 2x to the power of 2 all the time. I've sketched out 2x to the power of 4. 2x to the power of 6, we can guess, will be similar, but when it gets down, it'll be a little more extreme in that how it seems to flatten out and then how it seems to pick back up here. And the higher the power, if it's even, the more extreme that gets. And I'll show you the same sort of idea of what I did here in Desmos. So here's 2x to the power of 6. And here's 2x to the power of 60. It's an even number. And again, those may look like right angles. If I zoom in, you see they're not actually right angles. And the larger this gets, while it's still even, 600, 6,000, that really looks like a right angle now, but it's not. And so we see the same sort of characteristic. If it's a power function with a whole numbered even power, it has these same sort of features, but that's kind of I'm going to get back down to this. And so that leads me to everything except just the last one, negative 2x to the power of 7, which if you look at this compared to here, these functions should be the same, except because I have a negative in the front, all my outputs have swapped from being negatives to positives and vice versa. So now it's going to look something more like this. There we go. And so keep in mind, all these examples of power functions, please don't think they have to have a whole number power. We've been focusing on here if they're even or odd, but they can be any number. And so the last thing I want to show is if I just go back to Desmos here. Turn this off, turn this on. In general, as I just make n bigger, notice it kind of bounces back and forth depending if it's odd or even. You can have any, like this is a power of 16.2. We can have a power of, 23 whole or 24.4. But in the end, this can be any number, although at its simplest is when they're either whole odd or whole even numbers. And we'll talk more about power functions going forwards, but they are in many ways a simple function to write down, a coefficient, our independent variable, and some power. And that power is a constant, but it can be any number. I think I've talked enough now.